active mixers and some of their attributes. Uh, First thing that is very different from passive mixers we just covered in the previous session is that usually we can get gain from active mixers versus loss we got from the passive mixers. Um, it is very likely that in active mixer design we will need a lower LO power than we did when we designed active or passive mixers, because with passive mixer we were really looking at this as close as possible ideal switch performance, which here is less critical. On the negative side, active mixers will be less linear usually than passive designs. They will have higher 1 over F noise, since there is a DC current flowing in all the transistors during operation. When we design them, we will need a higher voltage headroom, so higher VDDs, which may become an issue in the modern technologies where really VDDs are going down in voltage. So this will introduce some challenges with active mixer designs, and especially in modern technologies. However, they do have some reverse isolation between input and output, which is a positive attribute. And because they are active, and this is a negative, we will need to consider stability again, and not only stability of the LO drivers as we needed to ensure before when we talked about passive mixers, but really the core here is more an amplifier and is potentially can become unstable, and stability of mixers is a big headache. It is not active mixers. It is not something one can discount or forget when designing a full receive or transmit chain or transceiver. Another difference between active mixers and passive mixers is that we said passive mixers were current driven and active mixers are voltage driven, as we will see soon, as they have a transconductance amplifier at the input. So we will start our familiarity with active mixer design by meeting a single balanced topology. So we have only one single-ended RF input to this M1, a common source transistor, and it's a voltage input, okay, that really transform the input into an output current. So M1, as we met in the when we talked about amplifiers, is basically a transconductance amplifier, and this output current of this M1 amplifier is really fed into M2 and M3, which in this case act as modulators, not necessarily switches as used to be with passive mixers, but let's treat them as modulators, which could be switches in part of the time, but more like large signal amplifiers, okay, at other times. And when we look at this topology, we just need to remember that M1 is a transistor amplifier that needs to be treated like any other amplifiers, common source amplifiers we discussed before. So we need to remember that its stability needs to be of course, taking into account linearity. As we analyzed before, we need to think about linearity of M1 the same way we thought about LNA linearity, for example, and noise figure as well. And the positive thing about this M1 that it does have some isolation between the input and the output, because between input and output there's only CGD, and if the gate drain capacitance is not very big, there is some isolation between input and output. And this is something that we didn't have with passive transistors. M2 and M3 are biased by half the DC current that is drawn by M1. So each one take 50% of the current in quiescent operation. But of course, when there's an input signal and when the LO is turned on, this pair will be functioning as a large signal differential amplifier. So we have a differential amplifier here. We can treat it as a large signal differential amplifier. And this pair will modulate the input that will be coming from M1, the input current. We can look at these two transistors as non-linear amplifiers. And unless the LO signal is very, very large, such that we can really look at them in switches, like switches. In this slide, we describe a double balanced active mixer that is actually two single balanced mixers that are connected such that the RF input is differential. We have two loads, and we have this topology with this cross coupling between the two single balanced transistors. Each side really work as was described before, and conceptually the mixer now will better reject the LO leakage, as we explained before, but not only that, but also, and more than that, the even harmonics, as we described with passive mixers. So this is actually one step before the full mixer, full differential mixer will be introduced. So we just took the two single balanced and we transformed it into a double balanced topology. In this slide, we complete the introduction of a double balanced mixer. We have added a current source that really make the input differential with common mode rejection. So DC biasing is really dominated by this current source. What we can see in this slide, and this is really a Gilbert cell mixer, as it can be found in the literature. What we can see in the slide is that if this is the VDD and this is ground, we have many transistors, like at least three. We have a common source, we have a current source here, which is usually a one transistor, but sometimes even more, and the transconductance amplifier transistors, and then we have the modulator transistors and the load, which may be resistive, but what we see is that we need to bias at least 1, 2, 3 transistors, and the output needs to be, if the output needs to be at around a half VDD or maybe 2/3 of VDD, we need to develop some DC voltage on these resistors, especially when we use it as a down converter where these loads cannot be inductors, then there's really limitation on how much voltage we can drop on each of the transistor. This is really becoming a challenge in the modern technologies where the VDD is dropping and getting to a 1 volt or roughly 1 volt total biasing voltage. I mentioned the loads here. Here we can see them as resistive, just to indicate that in down converters we cannot have inductors here because we cannot have huge inductors. So it has to be resistive, or it has to have some common mode DC voltage at the output. If we use up converter, these loads can be inductive, so this will help with the headroom challenge. However, inductors here, as we may have remember from discussing LNAs and PAs, will really pose some more stability issues on the whole circuit. So the whole circuit is, as I mentioned before, have a lot of potential instability sources. We have the common source amplifier here. We have two large signal amplifiers here, and stability is a main consideration here. But anyways, we see that the biasing of this topology with modern technologies is really challenging. So we have mentioned before that active mixers have voltage gain, and now we are starting to analyze and understand the voltage gain performance of active mixers. So when we do that, we can start with just a simplifying assumption for the analysis, and just think that we just take one side of the modulator as conducting, the other one is turned off, and we just looked at the whole mixer as an amplifier, where this transistor will be the transconductance stage, and these transistors can be considered as cascode transistors. And basically in this configuration, if it was an amplifier, then the voltage gain from input voltage to the output voltage could be very simply derived as GM of the transconductance amplifier multiplied by RL, the differential output resistance. However, this voltage gain represents amplifiers, and there's no mixing in this assumption. When only these two amplify and the inner two don't amplify, don't conduct, there's no mixing operation. If we want to mix, we need to engage signal at the LO that is taking 50% or as close as possible to 50% duty cycle signals on the LO and the complementary LO. And if we do that and we use similar analysis to what we did with passive designs, and remember to take the Fourier series of the LO signal, then we find very easily that the theoretical voltage gain will be 2 over pi times GM RL. This result, of course, assumes ideal switching, but it's already a good start to describe the potential for voltage gain. So if we have high enough GM or high enough load, resistance or impedance, then we can get voltage gain. In cases where we have practical LO, cases that were described in the literature and in papers, we have areas or periods in time domain where really we can assume that the mixer, the balanced active mixer, is performing like a ideal switching device. However, there are some transient times where the mixer operates as a large signal amplifier rather than a switch, and so the GMRL results are not really the full period but just part of the period, and really depends on the LO signal, how close this LO signal is to a square wave, and how high is the amplitude of this LO square wave. And so if we want to look at practical voltage gain, then we can find that the practical voltage gain is not GMRL times 2 pi, but rather we need to multiply it with another expression. And in this expression, we can find that, of course, if VLO, the amplitude of the LO signal, is very, very high, we are approaching the theoretical GMRL 2 over pi results we saw in the previous slides. Also, what we can see in this expression is that when VGS really equals VT, this will also be, or will approach 1, and we will get to the ideal result we got for voltage gain in the previous slide. However, VGS cannot really equate to VT, because if this happens, there's no current flowing through the modulating transistors, and if that happens, then there's no current going into the transconductance transistors, and so we cannot really operate at VGS minus VT equals 0. So the only way to really take this expression and make it as close as possible to 1 is to increase the LO voltage. And we said before that we don't have to do it. Okay, if we don't want to have a very high gain, we can still have a reasonably low local oscillator voltage swing, and maybe by increasing GM or allowing a higher RL or ZL, when we use a different load rather than resistive load, we can still have fairly reasonable voltage gain. Analyzing active mixer noise, can start with transistor M1, the transconductance transistor. When we talk about the noise figure of this transistor, we just mentioned we can treat it as the LNA common source transistor and use similar considerations there. But especially in direct conversion mixers, we also need to care about the 1 over F noise of the transconductance transistor. And so when the voltage on the modulators, the gate voltage on the modulators is exactly the same, okay, at these crossing point, the 1 over F noise of this transistor will be equal at the output, okay, and differentially will be zeroed. But this is just at these this crossing moment. All the rest of the period, the 1 over F noise of the transistor will be present at the output. And so if we want to minimize this noise, we need to look at the size of this transistor and just take it as a consideration and add it to all the other considerations we have when we want to choose M1, like linearity, current consumption, noise figure, um, stability. We need to add also the 1 over f consideration to the system of considerations we use. Of course, the GM and the current also plays a role here in determining um, the amplitude of the 1 over f noise. As we know, when there's no DC current or when GM is 0, the noise will be theoretically 0. However, we don't operate with 0 current in active design. So we know a little bit more about M1 design considerations now. We also need to take into account M2 and M3 that we mentioned before operate as a differential large signal amplifier, and they will also contribute thermal noise and also can contribute some 1 over f noise. So this we will deal in with the next slide. So the switching pair, in this slide we see bipolar transistors, but really the treatment is very similar to NMOS transistors. So the switching pair, Q1 and Q2, we mentioned they do add noise to the output, which is usually right at the drains or the collectors in this drawing. If we look at the times or the periods when one transistor is on and the other one is completely off, we can look at the full circuit as a cascade topology, and most of the noise will be contributed by the common source or common emitter in this slide. And actually the noise of the cascade transistor will be mostly degenerated by the common source transistor. However, within a period, there are periods depending on the voltage of the LO signal where both transistors are conducting. And when this happens, this is really a differential amplifier that has its own noise contribution. And so to minimize this noise contribution, we can try to increase the LO voltage, but it has its own prices. It will cost us more current consumption. We may put more challenges, stability challenges, as well as bias current consumptions on the LO buffers. So there's really a lot of trade-offs here. But we need to understand that this pair also contributes noise, and we can reduce this noise by maybe making the voltage of the LO signal larger if we can. Passive and active mixers have same system functionality but different performance and different performance attributes that designers must take into account and leverage and consider when they design and when they choose one topology over the other. Both topologies benefit from ideal local oscillator signals or close to ideal local oscillator signals, but in general passive mixers require larger LO signal amplitudes. And when we talk about the local oscillator voltage amplifiers or buffers, we should mention that even though we didn't treat it when we talked about mixers, these amplifiers or these buffers need to be considered as part of the full design and must take part in the full trade-offs, because they do consume a lot of current. They take cheap area, and they may introduce severe stability issues like every amplifier can do. And so it's not only their effect on the mixer core performance. We need to to see the LO buffers as circuits that have their own trade-offs and treat it as such. We cannot ignore the LO buffers. It would be a big mistake to do that. In modern technologies, we mentioned that the VDD voltage is going down, and it's becoming very, very challenging to have a simple Gilbert cell topologies as were described here, as we need to bias 3 transistors or more and still have headroom for biasing conditions for resistive load or for DC common voltage, and it's becoming very, very challenging. However, some people would still would like to take benefit of the active mixer topologies despite these VDD challenges and despite these dropping voltages. So hybrid topologies that try to combine between passive and active mixer topologies do exist and become more and more common, and people trying to overcome these dropping VDDs and still enjoy both worlds of good performance and lower VDD. And so folded mixers can be found more and more in mixers, and what we saw here in this in the last 2 sessions is basically we got some tools to handle these 2 kind of mixers, but we need to remember that we can combine the 2 mixers to enjoy both worlds. Thank you for joining me for the mixer active design session. This session has concluded the mixer design session in the seminar. Hope you join me for VCO or voltage controlled oscillator sessions that will follow on.